Then we will move forward to the second presenter, who is Luca Mao. He came all the way from Chile to present something to us, so that's very nice. So he and his group were using the total environmental simulator in Hull for an experiment that was carried out in 2012. We will listen to him to talk about the morphodynamic impact of vegetation and large wood in fluvial systems.
Thank you very much. So in this presentation, we are dealing about the geomorphological impacts of vegetation and large wood in big rivers, in braided rivers. So we are talking about gravel bed rivers, and in particular braided rivers, or multi-thread rivers. We know a lot about these systems, and most of these things we know are based on the knowledge of the interaction between water and sediments. But in fact, vegetation is a very important component as well. And it's not only vegetation, not only standing trees. When trees are eroded and transported downstream, they are called large wood. And they are large wood if they are big enough, and we usually consider them large wood as being longer than 1 meter and with a diameter coarser than, larger than 10 centimeters. And they can have a big influence on the morphology of braided rivers. In general, vegetation and large wood can influence the morphology of rivers, for example, creating scour pools or local, deposition of sediments. Hydraulic effects, especially they increase the flow resistance, but they can have a big impact on the ecology of river systems, providing habitats for fish, but also for birds and big mammals as well. On the other side, during extreme events, they can increase risks associated with the presence of vegetation and wood in rivers. But we don't really know enough about the complex interactions between the morphology of rivers and the vegetation, especially if we want to consider large wood as well. And we think it's a relevant topic because the way we tend to manage rivers now is we tend to give space back to rivers, meaning more space for vegetation, and meaning potentially more wood in rivers in the future. So what do we know? We know a lot about the effect of vegetation in rivers, either from experiments in flumes or numerical modeling, field studies as well. We have an increase in roughness, and vegetation, of course, stabilized banks. So there will be less space for the active channel. So overall, the channel will become narrower. On the other side, large wood tend to deflect the flow, so to concentrate erosion away from the gem. Usually these logs, they accumulate in gems. So we tend to believe that large wood can increase the width of the channels and create multiple channels. So from a morphological point of view, they will increase the braiding index, so the number of channels in a certain cross section. But we don't know how these two effects they balance together, and it's difficult to explore this in a real river because these two components are acting together. And there are no flume studies on simulating in a flume vegetation and wood at the same time. So we thought it would have been interesting to do that in a flume. And the main question is how these two components act together and how do they interact to express the morphology of braided rivers. And focusing more on wood, we want to know if the amount of logs in a certain reach is a good proxy for understanding the amount of wood coming from upstream, because nobody in the real river really know how many logs are coming from upstream reaches. Then the relationship between wood, the storage of wood, and the morphology of a braided river, the interaction between wood and vegetation, and the relative effects of these two components. So we thought it would be a good idea to do that in a flume. So we went to the total environment simulator at the University of Hull, and this flume is 11 meters long and 6 meters wide. So we divided the flume in 3 sub-channels. Each one is 1.7 meters wide, and we fed sediments, and we played with a steady discharge of 1.3 liters per second. We used uniform sand, D50 0.7 millimeters, and under these conditions we were able to develop a braided river, so a multi-thread river in a steady state condition. So sediment input is equal to sediment output. To simulate logs, the best we could think is to produce little woody dowels. They are 8 centimeters long and the diameter is 3 millimeters. The density is more or less the density of wet wood. And 40% of these logs, they have a rootwood as well. To simulate vegetation, we did as other people have done with alfalfa to simulate vegetation. As to the experimental setup, we did the first series of experiments with a couple of weeks in the 3 flumes, introducing only sand to develop a braided morphology on the 3 channels. Then we fed logs on the 3 channels with different input ratio, from 40 to 120 logs per hour, and we fed them every 15 minutes, not to provide them sort of in a clogged way. Then we removed the logs, we redeveloped the braided pattern on the 3 channels. Then on the last weeks of the experiments, we fed alfalfa in a channel, and on the other 2 we fed alfalfa, and also we fed logs. So to have a comparison of the morphology of this channel only with vegetation and logs together with 2 different input rate, 40 and 120 logs per hour. We took vertical photos, which were composed and allowed us to count, for example, the number of channels. We created some cross sections, and we counted the number of channels per cross section, and then we calculated an average value of the braiding index, and then to locate the accumulation of logs and the growth of the vegetation on the bars. And then we took laser scanner measurements of the dry bed at the end of each experiment. This is what we got in terms of accumulation of logs on the experiments when we fed logs at different rates. Of course, the accumulation is these curves, the number of stored log over time. These curves are very steep at the beginning, then they flat down. And the most important thing is that, of course, when you feed more logs, you have more storage, but this relationship is not linear. So it's not necessarily true that you can have a good approximation. The number of logs in a reach is not a good proxy for the number of logs that are coming from upstream reaches. And then we, using the vertical photos, which were taken every hour, we counted the amount of logs and gems which were at the same place over time. So we have a remobilization rate index for the logs and gems on the 3 experiments. What is interesting is that it's quite high. It fluctuates a lot, and there is no difference on the channels when we fed logs at different rates. And this is just a video to show you how it looks like. Does it work? Doesn't work. Well, yeah, you will see some logs moving, and suddenly one of these gems will collapse, and all logs will be released. So, using the vertical photos, we accounted for the persistence of gems and logs in certain positions. So we calculated these cumulative curves, and as you see, logs and gems they plot more or less similarly. Only for big gems, it's true that they persist longer. And the persistence is quite short, so it's less than 2 hours in 60% of the cases. And as you increase the time, the persistence will be lower. So our question is, why this persistence is so low, and is the morphology, the change of morphology dominating the persistence of logs, or is it the contrary? So we counted the persistence of anabranching and bars as well, using these photos. And the curve is more or less the same. So it's less than 40% in 2 hours, for example, meaning that is the change of morphology, the migration of the anabranches and bars to control the location of the logs and gems. So in fact, it's more the morphology changing the logs rather than the contrary. This is the braiding index, so the number of channel per cross-section in the channels with only sand, which is high, which is similar to what you can find in the field, around 4. And if you put logs, this braiding index won't change. So logs in general, they don't affect much the morphology of braided rivers. Then we seed this alfalfa. We did it during high flow, just to avoid alfalfa to grow on the main channel, for example. Then we lowered down the discharge. We left the channel wet anyway to allow the alfalfa to grow. We allow 1 week for the alfalfa to grow, and then we increased the discharge again, up again to 1.3 liters per second. And we fed logs as well, okay? And we did it for 4 weeks. In 4 weeks, the alfalfa can grow quite well. So now you see the channel with only vegetation, and the channel with the vegetation and logs fed at a rate of 120 logs per hour. As you can see, over time, vegetation is growing on the bars, but the channel with only vegetation appears more braided than the channel with the logs. And you can see that there are some big jumps here, but there is only one channel, even if it's wider. This is the braiding index for the channel with only vegetation. So the braiding index is reduced, but if you put logs as well, the braiding index is even more, even smaller. So the channel is more or less more or less one channel, one single channel. And then we use the laser scanner measurement. This is, of course, the measurement with vegetation. We had some troubles in filtering out the vegetation because in some points was very dense. But what we got is something like that, with the elevation of the channel and the bars. And the simplest thing we did was to analyze the distribution of elevation and to calculate the PDFs, the probability density function of these DAMs. The curve, this one, is for the channel with only sand. Okay, sand with logs, the curve is more or less similar, and as you as you feed, as you see the vegetation, over time this curve is moving toward higher elevations and is broader. So the simple way to characterize these curves is through the standard deviation of the elevations. What we saw is that if you fed logs, the standard deviation of the bed is more or less the same. So there is no effects on the morphology of a braided river. But if you add the vegetation, this C1 curve, the standard deviation of the bed is increasing, meaning that the channels are deeper. Okay. If you feed logs as well, if you feed logs as well, the standard deviation is higher, of course, than in the channel with only sand, but is lower than the channel with sand and vegetation. Okay, so the channels are a little bit shallower if you compare with the flume with sand and vegetation. So what we think we found is that the storage of wood is not a good proxy for the input of wood from upstream reaches, okay, which is something that could be interesting to know, for example, for designing check dams to trap logs. The remobilization of logs, it depends very much on the dynamics of the braided channels. So it's the morphology dominating the transport of these logs. Logs alone don't affect very much the braiding index or the topography of the bed, which was quantified using the standard deviation of the elevations of the bed. The vegetation itself reduces the braiding index and increases the standard deviation of the bed. And the addition of logs reduces further the braiding index, but the standard deviation of the bed is not so high. So the channels and the pools are not so deep as if you have only vegetation. Overall, there are many limitations of the study. For example, we had to relax a little bit the scaling because we were more interested on processes. Okay, and of course these dowels, they don't have branches, they don't resprout. Okay, but overall we think we are simulating something that reminds what you can see in the field. Okay, so we're pretty confident that we are dealing well with the processes, even if we can do a little bit better maybe in the future. And thank you very much.
Thank you very much. Interesting, very complex study. I think we're running a little bit out of time, but we have time for a few questions. Yes?
Yes, a question is, what was the length scale of, let's say, of these experiments compared to the prototype, and also for the sediment scaling? What was the dimensional number that you used for sediment scaling?
70. We used to use 70 for the grain size of the bed for the discharge, but for example, we couldn't use the same scaling for the logs. You see, the only thing we wanted is the logs were smaller than the width of each anabranch in the braided channel, just to allow the logs to be transported downstream without being clogged by the dimension of channels, which is what you can find in the field. But for example, the length of the dowels, it's higher than the length of the alfalfa plants. You see, so we had some little issues there, but the base scale of the braiding channel, the grain size of the bed, and the width, it's a factor of 70. Yeah.
Okay, thank you. Yes, I think that's it. Very good. Thank you for your presentation. So now it's time for the